we are going to evaluate limits analytically. This will be the main way that we solve limits, and we'll spend a lot of time on it and have lots of practice. So we are going to solve them analytically. Before we're doing it numerically and graphically, but we're going to talk about today, how can we use properties of algebra? I kind of alluded to this in one of our previous videos of using this idea of direct substitution, but also, if that doesn't work, how can I simplify or rationalize in order to use direct substitution? That's what we're really going to focus on today. So we have lots of properties of limits. It says let b and c be real numbers, and let n be a positive integer, and let s and g be functions with the following limits. So the limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is K. So many properties, they probably look similar to you in other topics that you have studied before. The first one is scalar multiplication. Remember, scalar means that we're multiplying by a number, right? Real numbers. So it's just saying the limit as x approaches c of b times f of x is the same thing as b times the limit of f of x. That one makes sense. Sum or difference, if I have the limit of the sum or difference of two functions, that's also equal to the sum or difference of their two limits separately. Product property, if I have the limit of a product of two functions, then that's also equal to the product of their limits. Quotient, same thing. Also, assuming that k is not 0, this works as well. It's very similar to the other properties we've been talking about. And last but not least, the power, which this one's kind of neat. If I'm taking the limit of a function to a power, that's the same thing as the limit to the same power. So let's use these properties to find or evaluate some of these guys here. So we're given that the limit of f of x is 3/2, and we're given that the limit of g of x is 1/2. So what I'd like you guys to do is I'd like you guys to use that given information and use the properties we just discussed to figure out what these should equal. So go ahead, put me on pause. So nothing too crazy about what we just did here. We were just using those properties. So for when we're multiplying by the scalar of 4, we should get 6. I should close my parentheses. Quotient property, we should get 3, because 3/2 times 2/1, which is 3. Here, my sum property would be 2. Product, man, I can't talk, is 3/4. This one is technically scalar still. You might think of that as division, which I mean it is dividing by 6, but it's the same thing as multiplying by 1/6, so we get 1/4. And then last but not least, that power property, we get 1/8. So let's add some fancy theorems to our list here. So it says limits of polynomial and rational functions. So think for a minute, what does it mean for something to be a polynomial? What does it mean for something to be rational? Okay, well, if p is a polynomial function and c is a real number, then the limit as x approaches c of p of x is p of c. I'll talk about this in a second. If r is a rational function, I wonder why they chose p and r. Anyway, that was dumb. If r is a rational function given by r of x equals p of x over q of x, and c is a real number such that q of c is not equal to 0, then the limit as x approaches c of r of x equals r of c, which equals p of c over q of c. Now you might be thinking, oh my gosh, first of all, why is she talking so fast? Second of all, what does this even mean? What this means is, what I alluded to in a previous video, is that we can use direct substitution if it's a polynomial or rational, assuming that the quotient, that denominator in the rational is not 0. Okay? As for both of these, we can evaluate the limit because, for example, polynomials, we know that they're continuous and they exist everywhere, right? There are no undefined values in polynomials, which is why we can use direct substitution. Again, and this is why we have this disclaimer here, we're assuming that q of c is not equal to 0. we can do the same thing here for rational. One thing else that I want to mention is that for the use of direct substitution, we can use that at any time, as long as we're not evaluating the limit where the function doesn't exist. Okay, the limit of a function involving a radical. Let n be a positive integer. The following limit is valid for all c if n is odd, and is valid for c is greater than 0 if n is even. So the limit as x approaches c of the nth root of x is the nth root of c. Again, this is using direct substitution, assuming that these conditions are true. So what this is saying, these conditions, is that if we have an odd root, we can always use direct substitution. However, if we have an even root, we can use direct substitution as long as we aren't getting an imaginary result. Okay, so that's what these conditions are there for. Okay, last one, limit of a composite function, or what I would call a composition function. Same thing. Let's say here, oops, should there be something under here? Interesting. Well, note that in your notes you guys have a theorem about the limit of composition functions, which we're actually going to use right now. So it says, given that f of x is 2x squared minus 3x plus 1, and g of x is the cube root of x plus 6, we want to find the limit of f of x as x approaches 4. We also want to find the limit of g of x as x approaches 21. And then we want to compose them, the limit of as x approaches 4 of g of f of x. And again, you can take a look in your notes at that theorem, nothing too crazy about it. So let's have you guys try this one on your own. Go ahead and put me on pause. Notice that I'm using what we just talked about. I put over the equal sign, I just put DS, which stands for direct substitution. You don't have to have that there. You'll see me sometimes put that in the notes videos just because I want you to know, like, what am I doing? I don't want you to be confused. So don't feel like this is something you have to do. It's just me. I'm trying to give you a cue as to what I'm doing. So I did use direct substitution here. F of x is a polynomial, so we just talked about that. So the limit of f of x as x approaches 4 is 21. Same thing here. The limit of g of x as x approaches 21. G of x is 3. And here, limit as x approaches 4, g of f of x. Well, first I figured out, well, what is g of f of x? Figured that out. Then I used direct substitution, and I got 3. Another way to do this is finding the limit of f of x as x approaches 4, which we did here, and then plug that into g of x, and evaluate that limit. I mean, that's the same thing. So I'll kind of walk you through this first example, and then I'll have you try some of the rest on your own. So I'm looking at this, I'm like, okay, so it's a rational function. And, my first instinct is, okay, can I use direct substitution? And if I use direct substitution, I plug in 2 for x in both places. Notice that I get 0 over 0. And I'm like, sirens are going off on my brain. I'm like, oh, crap, indeterminate form. Okay, so if that happens, then let's try to factor, do something with this to simplify and see if later we can use direct substitution. So this, okay, I can already see, I'm going to pull out a negative in my numerator. Then I get x minus 2, my denominator. And then I'm like, sweet, that rules. So now I just have the limit as x approaches 2 of negative 1 over x plus 2. Now can I use direct substitution? Sure. I just realized that this looks like a division symbol, and that's not what it's supposed to be. Alright, direct substitution, I get negative 1 over 2 plus 2, so I get, what the heck was that? Freaking me out. I get negative 1/4. And that is the limit. Okay? Now you might be thinking, well, what happened to the 2, x equals 2 in the original function? Because that is significant. Well, in case you were wondering, which hopefully you are, there's a hole there. there's a hole at the ordered pair 2, negative 1/4. However, just keep in mind that f of 2 does not exist because there's a hole there. We'll talk more about this later on, but that's kind of a little preview. Alright, so now that I walked through one with you, why don't you guys try the next one on your own? First, look, can I use direct substitution? If not, how can I simplify it to get to a point where I can? Go ahead, put me on pause. Alright, so hopefully right away you recognize that you get indeterminate form, so we can factor. And we get the factors of x minus 4 able to cancel out, which then allows me to use direct substitution, which gives me the limit of 1/2. Okay, so if you guys try this one. Start direct substitution, you get 2/0. And I want you to remember that this is not indeterminate form. And if that happens and there's nothing you can do with this, then it doesn't exist. Now, again, you might be wondering what happened at x equals 1. Well, at x equals 1, we have a vertical asymptote. Just as a little side note. Alright, let's have you try this one. As a hint, you will want to multiply by the conjugate of the numerator. That will help you. So go ahead, put me on pause. So immediately I look, can I plug this in? No, I get indeterminate form. So my hint to you is to multiply by the conjugate of the numerator. So I do that, and then I simplify a bit. I get x over x times this whole quantity. You might be initially inclined to distribute, but sometimes it's nicer, you'll find, to not, because these end up canceling as well. So now I get to a form where I can actually use direct substitution. When I do, I get 1/2√2, or that's the same thing, rationalized, √2/4. Alright, another example. Let's have you guys try this one. I'm not going to give you a hint. Haha. Okay, go ahead, put me on pause. So again, I found that I would have indeterminate form. So what I did, and this was what I was going to give you a hint, then I became mean, was I multiplied by the least common denominator of the numerator, which is x plus 4 times 4. When I did that, now, if you're confused about the algebra part of this, then you need to actually multiply this all the way out and show more work. So that way you can figure out where I got this from. But when I do that, I get that these terms cancel out, which leads me to my next step, but then also these terms cancel out. Make sure you guys always show work. Which gets me to a point where I can use direct substitution, and I get that my answer is -1/16. So, try direct substitution first. Always look. Okay? If the limit of f of x as x approaches c results in indeterminate form from direct substitution, then we have to try to divide out common factors or rationalize the numerator, so that way we can use direct substitution. And you can always use a graph or table to reinforce the results.